Okay. We're getting right down to the end. Reminder that the final is 2 weeks from today. So not much left. We really only have 3 more days of new material today, next time, and then the following time. That's and after that will be the review and then the test. So getting right down to the end. So today we're going to finish out chapter 22. Now we've been going and giving all sorts of functional groups and how to name them, things like that. We have done all the functional groups, so we don't need to add any more functional groups. That's done. Section 4, we're going to talk a little bit about some more reactions, some different types of reactions. The first type is an elimination reaction. So elimination reactions, well, obviously, we're using the word elimination, we are going to be eliminating something. We're getting rid of something. And that can actually be a couple different things. The first example, so if we have ethane here. What we can do is, well, we can get rid of that hydrogen. So we're going to have hydrogen gas. And then, so if we get rid of this, we have left is that, but that's not valid because these carbons don't have enough electrons to fill their valence shell. What happens is, okay, so remember there are 2 electrons in each one of these bonds. One is going to come down into each one of those so that we can have that. These 2 are going to jump up into there to form a double bond. So we lose the hydrogen and we're left with ethene instead of ethane. So this, because we're getting rid of hydrogen, has a name, dehydrogenation. Dehydrogenation. You take something that has, it doesn't have to be fully saturated, but it has to have at least a single bond that can collapse down into a double bond when we lose the hydrogens. It's also possible, for example, if instead of a hydrogen there, well, let's say we have fluorine, we can do the same thing. Obviously, this is not dehydrogenation because we're not getting hydrogen gas, but it's still an elimination reaction following the same path. So we also, if instead of fluorine there, clean this up just a little bit here. So if we're dealing with an alcohol, Well, we can do the same thing. We can pull these two off. We are going to end up with the double bond. But here, so we have two hydrogens and one oxygen. Water. This is a dehydration. Dehydration. So we're pulling water out of something that doesn't have water because we're pulling the components out and we get that. So elimination. Pretty straightforward. If you are pulling something out of the molecule, we've got elimination. If we go back to our early days of chemistry, this would fit the pattern of a decomposition, where we're starting with one thing and we're breaking it apart into different pieces. So, elimination. We can also go the other direction. Instead of elimination, we can have addition reactions. Now for addition reactions, and there is a summary of all of these on page 804. Since we're adding something, we have to start with a molecule that can accept something. And so we have to start with a double bond. If this were fully saturated, by definition, we can't add anything else. We can't just add. Since it's unsaturated, we can. And basically, this is just all the opposite things that we can do. Okay? All of the opposite. So if we add water, this is a hydration. So we're going to get rid of the double bond. And we still have, so this is everything that we started with. And then this, we're going to break it apart into a hydrogen and an hydroxide. So we're creating an alcohol. We take an alkene and hydrate it, so this is hydration, we create the alcohol. If we just do hydrogen, changes to that, pretty straightforward. Okay? It's just the opposite of dehydration or dehydrogenation. This is hydrogenation. This is something that we do with foods. So if we have oils, which are carbon chains, and they have these double bonds, so we have the unsaturated oils. The problem is they can react with a whole bunch of different things, and if it reacts with something that, well, isn't fun to eat, like sulfur, that makes the oils go rancid. They're not, makes the whole food spoil. So what they can do is add hydrogen to these oils to fully saturate them, and it gives them a longer shelf life. Hydrogenation. And of course, if we have, let's take iodine this time, we have a halogen, then with that, it also is possible going this direction, do that, and we get something like that. Those are all addition. Okay? This would follow the pattern of synthesis from our earlier reaction types. Just as a comment, we can start with an alkyne, the triple bond, and at that point it would go from an alkyne to an alkene. So that is a possibility. And then of course you could do the same thing again with the alkene. With hydrogenation, we typically need to use some sort of catalyst because it doesn't like to happen on its own. The activation energy is just too high, so we tend to have to use a catalyst. Of course, the book does go on with a few more. And redox. Okay, these molecules can do redox. Obviously, oxygen is often a big part of redox. Where the ox comes from, honestly. So we can add oxygen here and there, and that's those are redox reactions. They are listed on 806, but honestly, I'm not that concerned about redox. We've just done a bunch of redox, so we'll stick with the other stuff for organic. Okay. When you, it's talking about predicting. Honestly, it just kind of takes a little bit of practice with things like addition reactions. I mean, you just kind of have to take what you're adding and put it on. Okay. We talked a little bit earlier about substitution reactions. If you have fully saturated and you know that you have to react something with it, that's when you know you're going to be dealing more of a substitution because, well, you said if it's saturated, you can't add more stuff to it. So, okay. So that's section 4. I'm going to finish out with section 5. Section 5. Section 5 is called polymers. Polymers. So we've got this prefix of poly, and that means many. And so what we have in a polymer is many molecules that have reacted and been chained together. Now these form really, really big molecules. So just as an example, water, one individual water molecule, has a mass of about 18 AMU, atomic mass units. We can get polymers that have masses of over 1 million AMU. So we're talking much, much larger molecules. And we don't want to have to draw out something that has 1,000,000 AMU. So we have come up with a shorthand. Remember, we're making chains. We're making these chains of molecules. And each one is going to look the same. So here we've got this, and all of them, they look the same. And when we have a polymerization, that's what we call this reaction, we take one and it attaches together. And then another one's going to come. It's going to attach together. And another one. And it makes this long chain of repeating units. So to write that, really all we have to do is write the one unit. Okay? You can see the example of how it does it. It gives the example of polycarbonate here in the book, which is used for optical discs, CDs, DVDs, things like that, which are becoming less and less common. But anyway, so what it shows is we've got benzene, another benzene, and it puts it in these brackets, a little N. And what that says is N, however many. We don't know. And honestly, we don't really care how many. We just know that on the other side of that bracket, it's going to start over. And we get another one, and another one, and another one. We can have them over here too. Right? So we've identified the simplest repeating unit. These are polymers. Now, polymers don't have to be man-made. There are actually a lot of natural polymers out there. Things that you eat have polymers in them, like starch. Starch is a polymer. It's repeating subunits of glucose. Wool. Wool is a natural polymer. DNA. DNA is a natural polymer. So the key for polymers is you've got this repeating unit. Okay. So synthetic polymers, obviously if it's synthetic, that means humans are making it rather than nature. But anyway. Some vocabulary. This right here, the repeating unit, is called a monomer. A monomer. So mono means one. So that is the monomer that is repeated over and over and over. And of course, as we said, when we do this, this is called polymerization. Okay? polymerization, we're making the polymer. There's a couple different ways that we can do polymerization. One is addition. So we just add them together and they go on their merry way. But sometimes we have something called a condensation polymerization. And that is basically if we have two things that come together, often what's going to happen is, so we have hydroxyl groups on both sides. And so what's going to happen, we get that leaving as water. We end up with this. Okay, so that's condensation. Then of course we can add another one here to do the same thing, and another one and another one. So sometimes when we do a polymerization, water is one of the products. And we get one water molecule for every new addition to the chain. Now, there are on page 812, 8 different common polymers. It gives you what their name is, what they can be used for, and then the actual structural unit. I'm not going to expect you to memorize those. But one thing that I do typically say that you need to be able to do is to pick them out. Pick out the monomer, is what I should say. So basically, if I were to give you this entire thing that we wrote here, be able to pick out what the repeating unit is. Okay. So that's pretty much what I expect you to be able to do. When it comes to polymers, some of them have different properties than others, depending on what happens. One very, very common polymer in today's world is just plastic. So pretty much any plastic is going to be some sort of polymer. And when we talk about plastics as polymers, we can break them into two different groups. So if we call it a thermoplastic, basically this is something that is easy to be recycled. If we have a thermoplastic, we can melt it down and reform it into something else. However, a thermosetting polymer, once it forms, if you apply heat to it, it's not going to melt. It might start to break down chemically and it could burn and do whatever, but it's not going to melt and allow you to reform it. Right? So that makes it much more difficult to recycle, but it is a good characteristic for certain applications, certain heat applications, because if it's going to be in heat but not hot enough to make it decompose, then a thermoset is exactly what you want. So because of that, that's why different plastics have that different recycling number on them, so that they can be separated into their appropriate categories. But yeah, so Now I do have an example of a polymerization here. So we're going to do this polymerization. So obviously this is kept in two different containers because, well, once you mix them, the reaction starts. So you can't mix them until we have them where we want them. Stir here. So we're starting to get these two different chemicals that we've separated starting to react. And it starts out slow, but if you watch, it now is rising, yes. So part of this reaction generates a gas. And the gas is released, but as these molecules are reacting with each other, they are basically trapping the gas in these bubbles. And so we get a foam. This is, if you're familiar with expanding foam insulation, this is essentially what that is. It's polyurethane, so it's polyurethane foam. And also the reason why it's not pouring over the side of the cup is because of the polymerization reaction. We're getting these molecules that are making these really long chains, and they're solidifying. We're getting a bunch of cross chaining and things like that, so that it's creating a solid structure. It'll take it a minute to fully solidify. But you can see it's not a really soft foam. Okay? Right now it's soft enough that I could shove something down through there, but in just a couple minutes it's actually going to be completely solid. It is exothermic, so the cup pretty hot. Obviously not hot enough to melt the plastic, but definitely warmer than it was. So that will probably continue to grow just a little bit more, but it looks like it's pretty much done. So polymerization, we've got the real world example there. It works really well as an insulation because, well, it's trapping all those air bubbles, which is really what you want with insulation. It also expands to fill up the entire area. With other forms of insulation that you lay in, you kind of have to work to try and get it all throughout the structure. But with this, it does it for you. You put in a thin layer and it will expand to fill whatever you need. And then you just trim off the excess. And it works pretty darn well. So anyway, polymers. Polymers, long chains, they're really, you find them all over the place. In plastics, natural polymers, in our foods and things like that. So yeah. Anyway, that is the end of chapter 22. The end of chapter 22. Like I said, we really only have 2 more days of new material after today. We're pretty much finished with this chemistry class. So that's where we'll stop for today. And I actually am giving you a break from homework today. So if you have any old homework that still needs to be done, you can work on that. But yeah, just today is a homework break day. So.